So printing, see what happens is, I don't even know. So, well, dumbware reduce marks. I don't know. Okay, what TS are doing about it. Don't worry about it. You know, you lose 1 mark here or there. Rhythm. Every mark matters. Huh? Lost many in DS. So you lost many in DS and DSM. So you want to make them up in C programming course. Huh? Interesting. Yeah. So, okay. 10 CGPA, me too. Okay, enjoy, guys. Okay, I'm not in that game. So anyway, so the thing is, of course, you can printing onto the screen, reading it, in the transpose, all these things, they are all right. Maybe for this homework, but in many computational problems, you want to use the A transpose matrix in some way. Okay, then if you just print it, how are you going to use it? All geniuses in the class. I'm sorry. Huh? So because there will be some sequence of computations in a bigger program. We print and scan the same. Vinkesh, awesome, man. Print it, then scan it again. Okay. Great. You're really awesome. No, it will work now. You can print it and then read it again. When you store it in another matrix, then when you are storing it in another matrix, that's not the thing. You read it into the same buffer. No, it's just like very simple now. You just print it into some file, or it's equivalent to, you can, when you print it, means you, instead of writing it into memory, you write it to hard disk and then read it back in a different, you write it to hard disk, the transpose, you write it into the hard disk column wise, and you just read it. It works. It works. Yeah, it will still work. It depends on the compiler. Compiler may complain, or you can use. If you use pointers, it doesn't matter at all. Okay, so Gaurav, can you explain? I will share. You can share the screen and you can explain to all of us how you are doing it. I'll stop my screen share and I'll have, go ahead, Gaurav. Yeah, I'm serious, Gaurav. Yeah. Oh, beautiful code. You can, I will, please raise your hand. I'll let you unmute you so that you can explain your code to us. Gaurav is here, asked to unmute. Okay.
Good afternoon, sir.
Good afternoon, Gaurav. Yeah, please go ahead.
Sir, so what I did, as the matrix will have two dimensions,
Hmm.
I choose the dimension which is higher, like
Hmm.
greater, and I made a square array out of it. And then I used the program I used for the previous question, and then I just printed it to a limited number of rows after swapping.
Okay, okay, okay. Okay. The strategy works, but the memory required is not strictly MN. It is
So it is
mag,
MM, like the greater
MM, where
one.
M is the max of it. Okay, got it. Yeah. Understood your strategy. Thank you, Gaurav.
Thank you, sir.
No, here. So you understood Gaurav's strategy, right? He's kind of instead of using a two matrices, is saving some space by allocating a bigger data structure. Okay, anyway, this problem is all right. Let's go ahead and work on Gaussian elimination. Okay. Okay, if we can use just M by N memory and transpose it in place, ask Gaurav, then that would be yeah. So Gaurav's strategy is good, but other more challenging question is just use an M cross N matrix and still work with it. So of course the problem, some of you are getting puzzled that how is it even possible. So one way of thinking is you just let's say you just have int star A and you say A is equal to malloc. So you have an array of this is malloc size of, just pay attention to what I'm writing here, m times n times, this is the memory that we allocate. Oh, I'm not sharing screen. Huh? Okay. So do you see here? So one so one way is you just allocate mn memory necessary to store mn integers. Are you with me here? Using these pointers and dynamic memory allocation. So, okay, using pointers and then after that, you try to kind of work with it in some way. Yeah, that the thing here is overall there are mn elements. We want to change the layout of the elements here so that the layout looks like for A transpose rather than A. Anyway, this is, think of it as a challenge problem. We will move on because I want to talk more about Gaussian elimination method. So first question for you, how many of you actually referenced this link that I gave in the assignment? Because everything that is required is there actually. Watch it, the videos are also there. It's not so if you see this one, then even more than Wikipedia here itself, this is very good thing. So if you see, Gaussian elimination method, I'll just review here. What is the goal? Our goal is we would like to solve a system of linear equations. So we have n equations and n variables. And if you write it in matrix form, this is like the coefficients A1 and we and then so on A21, A2n, AN1, ANN. So this is, and x1 to xn is equal to b1 to bn. So this is called as ax is equal to b. This is where x is a vector and b is a vector. So the system of linear equations, we can write it in this particular form. Ax bar is equal to a times vector x is equal to vector b. Are you with me here? First step. And from your intermediate or high school, so if you take this one linear inequality and one equation and add it to the next equation, the system of linear equations remains the same. The system of linear equations remains equivalent. The system of linear equations remains, this is row R1, this is row R2. If the new row R2 prime is equal to R2 plus R1, then the system of linear equation, then the new system that we get, it has the same solution space as the previous system. Or if you do something like R2 prime is equal to minus R1 plus R2, then also the new system will have the same solution as the previous system. And if you keep repeating this, then if you generalize it, then this is something like, R2 prime is equal to CR1 plus R2, where C can be any constant, positive or negative integer, then it's the same. Okay, the new system that is obtained by replacing row 2 by doing that row operation, that system has the same solution as the previous system. Are you all with me here? So this is the basic idea. And one interesting thing here is, when you do this row operation and when we obtain a new matrix, the determinant of the new matrix is same as the determinant of the previous matrix. That means as long as we keep doing the row operations, the determinants just remain the same. It's not going to change. The determinant of every matrix that we obtain in this series, it will be the same. That is one important idea we should keep in mind. It will be useful. It will not be, we don't use it in the Gaussian elimination method, but it is useful for determinant computation. And then, so what do we do? So clear. Yeah. So we take this one and we try to, you're not, okay. And then we try to do a series of row operations. We do a series of row operations and we finally obtain the final equation. So sorry, we finally reduce it to a upper triangular matrix. We reduce it to an upper triangular matrix. So here, let's see, let's go here. Let's take an example. Yeah. Can someone give an interesting example matrix, 3 by 3 matrix? I don't think I'll be able to work, but at least yeah, maybe let's take this example itself. Okay, this is the example that we have. Pay attention here. This is a, we have a system of 3 equations. We have a system of 3 equations, and this is how the equations are looking like. And so what is our goal? We want to, in the first operation, we want to multiply row R, we want to multiply row R1 and add it to row R2 so that this element 64 get zeroed out. So what should we multiply row R1 with? Minus 64 divided by 25 into row R1. We add it to row R2. Yes or no? Similarly, in order to zero out this 144, what do? We do minus 144 divided by 25 into row R1 and we add it to row R3. Okay, so this one goes to row R3 and this one goes to row R2. We add this. And during this process, what happens is, this 64, the element, this becomes 0 and this becomes 0. And actually what we do is, as we are doing this process, we can keep track of what is happening by making use of a matrix. So 1 0 0, 0 1 0, 0 0 1 have a matrix like this: 25 5 1, 64 8 1, and 144 12 1. So when we do minus 64 times 25 row 1 and add it, we apply it in this first matrix also. Then after transformation, what happens is this matrix looks like minus 64 divided by 25, 1, 0, 25, 5, 1. This becomes 0 and this becomes, I don't know, some values. Similarly, when we multiply the first row with minus 144 divided by 25, this gets encoded here, and then this becomes 0, we get this matrix. So the first column gets zeroed out, the elements in the first column get zeroed out, and this is what is called as a pivot element. And then we repeat the same process for this. Okay, so we want to, this is the pivot element, and we want to zero the element below it. I think by this time, all of you have read it and solve this problem. But what I would like you to keep in mind is, when we are doing LU decomposition, it keeps track of the operations that we are applying. Finally, that becomes the L matrix. So you start with A and so what we do in practice is, so we have this thing AX is equal to B. Maybe let me share the white screen, whiteboard. So we have the matrix AX is equal to B. So from this, what we do is we have, we construct this augmented matrix. And actually from here, we get we put A, I, A, B. Okay. And so let's say if you have, can someone give me some nice matrix, easy matrix to work with? Maybe easy equations to work with. We can try it out. 1 0 0. That is 1 1 1. Yeah, 1 1 1 2 1 0 minus. I would like to have an or anyway. Okay, let's try this out. Why not? So the original matrix is 1 0 0. Sorry. 0 1 0 0 0 1. I don't want identity matrix. Stages has some interesting matrix. I don't know whether it will work or not. Let's see. 1 1 1 2 1 0 minus 1 3 2, and maybe I'll just keep B. So this is B, this is A, this is identity matrix. So what is the first row operation that we would like to do? 2 times first row minus 2 times first row and add it to the second row. Yes or no? 1 0 0. So when you do this, the first row remains the same. The last column, I'm just assuming, no, this is the right hand side unknown. This can keep changing. Like for example, if you think of that x plus y plus z is equal to 1, 2x plus y is equal to 1, minus 2x plus 3y plus 2z is equal to 1. So we have 4 columns. This is B and this is A. Yeah, we want to use, I'm solving the Gaussian elimination problem and LU decomposition simultaneously. Because when you do the decomposition, finally, I think you get L here in this matrix. Okay, so like minus 2 times now, yeah, I think that's what will happen. We will see. We'll see. Because essentially what we are doing, yeah, okay. So now minus, yeah, 4. Are you with me so far? Are you all with me? Yeah, 3. So minus 2 times first row and add, we get minus 2. This will 0, 1, 0. And then this is 0, minus 1, minus 2, minus 1. We can record the matrix operations in the left matrix. Yeah. That is the L matrix. I think we should get to, where should we get to? Here. Okay, I think there is a small way to fix it, Abhinav. See, essentially what happens is the story is like this. Okay, so we apply a sequence of E1, E2, E3, a sequence of elementary operations we apply to A, and finally we get U. So what happens is then A is equal to, we have to record it in a different way. So A is equal to E1 inverse, E2 inverse, E3 inverse into U. So essentially, in order to get this, we can get this matrix by this L matrix. This is the L matrix actually. We can get the L matrix by recording it in a different way. Then we should be able to get it. So even E2, E3, these are all elementary row operations that we are performing. There's a way to fix it. Okay, you just took L as a separate mat. No, you just took, I'm just giving a logical view. So would inverting be anyway? So maybe let's do one thing. I will, in order to get this L matrix, there's a small trick we have to perform. But let me give you the big picture, and then we will see how we can solve this. Okay. So now, what is the next operation that we have to do? Can someone help me? You just add row 1 to the last row, then we get 1, 0, 0, 0, 4, 2, 2. This is the matrix that we get. And what's the next operation that we have to do? 101. No? Oh, sorry. What's the next operation that we have to do? We add row 2 to 4 times row 2 to last row. 1, 0, 0, 1, 1, 1, 1, minus 2, 1, 0, 0, minus 1, minus 2, minus 1, 4 times minus 8, minus 7, 4, 1, 0, minus 8 plus 2, minus 6, minus 4 plus 2, minus 2. Okay. So anyway, so let's see if you kind of keep, for the time being, if you keep the first thing aside, if you just focus on this, we got this upper triangular matrix, right? Yes or no? Are you all with me that how we got this upper triangular matrix? And once we have, this is what is this step called as? Forward elimination method. Okay, this is called as forward elimination. What is the next step that we do? So the system of equations that we got from this, what is the system of equations that we have right now? So we have x plus y plus z is equal to 1, minus y minus 2z is equal to minus 1, minus 6z is equal to minus 2. So now we do the backward substitution. Z is equal to 1/3 and y is equal to whatever we can find out y. If you know y and z, we can compute x. So the next thing that we do after this is step 1, forward elimination. Step 2 is back substitution. So all of you, so and the code for this, it's not very difficult. Yes or no? We just require 3 loops. It's not very difficult to write code for this forward elimination and back substitution. You just have to think a bit, because since you are new to programming, it takes a little bit of thinking, but otherwise it's not difficult. So those of you who didn't do it, will you be able to write code for this? For n variables, you require n loops. No. Why do you need n loops for n variables? What should you do? So first, what is the broad big picture here? If this is your matrix, so what should be the shape of, what should be the structure of the matrix after the first? So you have to write a loop in which in the first time you take this element as the pivot, and 0 knock off the first column. Are you with me here? You take the first element as the pivot. This is what is called as a pivot. We knock off the first column, so we get 0, 0, 0, 0. So what if the first element is 0? So let's not take that case. We have to do a row exchange. Yeah, we have to do some kind of row exchange, not continue. We have to do some row exchange to do it. And then after that, what happens is we take this element as the pivot and knock off this column. And when you do that, the structure of the matrix will be like this. Okay, all zeros, 0, 0, 0. So you need to write a loop. In which in every iteration, so this loop goes from 0 to I less than n minus 1, knock off column I. Does this make sense? You go from I is equal to 0, you knock off every column. And knocking off column, can you do it using a single loop or you need a 2D loop? If somehow, then it's a difficult problem. So maybe, that problem we can keep aside. We have to do, no, it can be 0. We can use, let me stop. Since many of you are watching elimination, yeah, I will share the screen. Do you see this? Do you see this algorithm? Just a, so in this algorithm, so in this loop, you see this loop, the J loop. So the J, so we start with first column, we go to second column, we keep going to n-1th column. Nth column, we don't do anything because by the time we come to nth column, this is the element that we get. So we don't need to do anything. Are you fine with this one? Are you all fine with the outermost loop? And then, so when we are in this column, we have to consider, when we are in column 1, so we have to consider row 2, row 3, row 4 till row n. Yes or no? When we are in column 1, we have to consider row 2, row 3, row 4, row 5 till row n. And similarly, in general, if you are in jth column, so we have to work from row j plus 1 onwards, right? Because what happens is when we come to row 2, so the submatrix that we have to consider is this. And when we come to row 3, the submatrix that we have to consider is this. When we are here, the submatrix that we have to consider is this. So what we do is we start with row, when we are in row 1, we start with row 2 and this side onwards. Okay, and the column is also given by, so which column you start? We start with row 2, column 2. Here, this is the place where we start. Okay, approximately, this is what is happening. So the way you are going to, so you initially process this this matrix and then you keep going like this. Are you all with me here? Does this code make sense? And here, this is the pivot computation. Can you take this code, and those of you who have trouble, can you take this code and write it up and understand it? Are you all with me here? So you got some idea about this code? Do you think you will be able to write code for this today in the I don't have check. I just copied it. I just searched for it and what do you mean it's a paid service? Huh? Oh, okay. I just searched for Gaussian elimination because this is a very standard algorithm which you can get it anywhere. You are not doing sufficient research, guys. Research is just not, you can rediscovering things also is research, but don't copy paste, but okay. Yeah, wiki page. So wiki page, I'm sure Wikipedia will also have it. Yeah, this is a very so standard thing, even wiki will have it. So let's see Gaussian elimination algorithm Wikipedia. How do we do swap rows? No, you just, how do you swap rows? You swap element after element. Okay, so you have beautiful example here. See, the whole thing is so nicely given. This is the pseudocode. Okay, now let's get back here. So in any case, so you do the forward elimination, you do backward elimination, backward substitution. So one interesting thing here is, so number one, are you all with me on the Gaussian elimination algorithm? Yes or no? Okay, number one. So in Gaussian elimination, it has forward elimination and backward substitution. And okay, so the other thing is when you are working with numerical methods, you get into lots of problems. We have to be careful. So for example, in this, if you have read this write up carefully, during the computation, if you use 6 digits for, if you store 6 digits after decimal, then the solution that you get is, this is the solution that you get. And the exact solution is all ones. Are you with me here? Because of rounding errors, when we solve the Gaussian elimination, this is the approximate answer that we get, and whereas this is the exact answer. In this particular case, one of the reasons why your TAs have trouble putting everything on OJ is, OJ is designed to check solutions exactly. Okay. So it's not like, some depending upon the precision you use and variety of factors, the answers will be close by, but it will, so the answers will not be exact depending upon the precision. So here, when you use 6 digits, this is the answer we got. But then if you use 5 digits, then what happens is, let's go back, go down and see, then the answer we get is this one. Okay, if you use 5 digits to represent the after decimal point. Are you with me here? Or you all, did you see what is happening in the screen? So here, if you use five significant digits, the answer due to round off errors, we are going way off. So, but when we use six digits, 6 significant digits, then the answer looks very close to the exact solution. So usually round off errors occur. And other thing, of course, is some of you already asked this question. So during the process of elimination, let's see, there are, yeah. So here, this is one more question. So during the process of elimination, if you get a pivot as a 0, so here in the first step itself, you got pivot as a 0. So how do we solve this problem, the divide by 0 problem? So here you got it in the initial step itself, but sometimes during the process of elimination, you finally get one, you may end up getting 0 in the intermediate steps. What do you do? So here, what do we do here? We can swap this row with this row and work with it. How can we swap 2 rows? We can you write code to swap 2 rows? Yeah, it's not difficult. You can swap 2 rows. So whenever you get a 0, you have to swap it with a row which is below it. We have to add a row just below it. We have to add a row below it, not above it. Swap with some other row below it. Are you with me? Like for example, here, while processing this particular submatrix, you got a 0 here. So you go down here, you go down and you try to find a row with a non-zero element and you swap these 2 rows. Does this make sense? No, we have to, when you get a 0 pivot, you cannot knock these things out, right? You don't need malloc at all. If you want to use the pivot element to zero out things below, but if you have 0 here, you will not be able to do it. Yeah, I told the TS to go easy on you, so. So anyway, do you understand the problem? How many of you are with me? So there is, you want to use the pivot to zero out, but then if there's a 0, then you have to go down and try to find error and swap. Second, so this is one problem. Second problem is if you keep going down, in the process of elimination, observe this matrix. So you are getting a very small value as a pivot here. When there are small values as pivot, your problem becomes numerically unstable. Okay, so there is this technique called as partial pivoting. In partial pivoting, what we do is we try to find a row with the largest value in that particular column. So here, if you check these 2 rows, the third row has one value 1 and this is 0.001. So we want to swap this because we want a big value, the pivot as a big value. We want a big value as a pivot. Because small values, when you they cause numerical instability when we divide by small values. This is called as partial pivoting strategy. Put it in another way, you can combine partial pivoting and handling 0 in the same way. Yes or no? How do you do? Let's say this is your matrix and this is your pivot. What should we do? Check for max element. Excellent ones. That's all. So we keep going down and we find a max element. Let's say this is the position of the max element. Whether this is 0 or whatever doesn't matter. You go check for a max element. If this is the max element, then you take this row and you swap these two rows. That's it. In single shot, your zero problem and this idea of partial pivoting, it will be taken care of. So you can take mag's absolute value. Absolute. What is all zeros in the column? I think you can just leave it. If it is all zeros, it's not perhaps it's not an invertible matrix. Okay. Can everyone solve this problem now? Gaussian elimination method, those of you who are struggling, can you sit today, tomorrow and try to solve this? Okay. So now if you are able to solve, what do I say, this problem, if you are able to solve the Gaussian elimination, then what happens is, you go at the end, they say, there is this theorem, you let A be a matrix and, then if B is an n by n matrix that results from adding or subtracting a multiple of one row to another row, then both the determinants are the same. Yeah, there is CPRO lab. And the determinant of a lower triangular matrix or upper triangular matrix is product of the elements along the diagonal. So you solve the determinant problem also. And this is a polynomial time algorithm to compute the determinant, whereas the algorithm that we used using the cofactor approach, that takes it's an exponential time algorithm. So you solve this problem, determinant is given for few. Can you talk with your TS and try to see what's going on, Rohit? Okay. Did you get to watch Gilbert Strang's linear algebra videos, first 3-4 videos about LU decomposition? See, I see if you watch those videos, LU decomposition videos of Gilbert Strang, then you should be able to do LU decomposition by yourself. And also, not only that, in this book itself, there are associated videos. Did you watch them? Very nice videos associated with this book. See, when you go to hear more, where is this book? This is the book I posted as a part of assignment. Okay, if you just go here more, this is very, it is there, it is. No, you just have to look careful. You just have to copy this numerical methods and then you'll get it. Now, if you go here also, you'll get it actually. Anyway, so what else? Okay, what else? Gauss-Seidel method you are able to do? Gauss-Seidel method. Didn't do it. Gauss-Seidel method is so easy. You have a system of equations. You have x1 x1 you write it like this, x2 you write it like this, so on and so forth. And you start with an initial estimate of x. You keep trying again. You keep resubstituting. You get better and better approximations. That's all. And given an array of matrices, how do you transform it into this form? This is also what you have on the right hand side. No, you can represent it as a matrix. No, answer is not matching. That's not the point. The answer that you got when you substituted it in the system of equations, what is it that you are getting? Okay. We keep iterating until now we are happy with some the error is small, some notion of error we will have. If that is small, then we will. Okay, last, this is, I will not discuss, I'll post one more video for this one. For the power method, did anyone solve this problem? The power method to find the eigen value of a square matrix. That's a very interesting problem actually. If you know the theory behind it, you will really enjoy that problem. Okay, I will post couple of videos, very nice, 2 short videos for this. After that, you should be able to solve it. Okay. When is the deadline? We're not extending the deadline, guys. We are not doing the, you have to do. I don't think deadline extension is any. How do we get initial estimations? Anyway, don't worry, but it's, independent of OJ, my question is, are you working hard? No, you got lot of time, right? Yes or no? Isn't it? I'm just trying to find the links for you. Lot of time. Okay, I'll post the video to you later.